It is permitted to run conduit between two busway disconnects and then feed to one common conduit run to feed two three-phase motor circuits. This is in accordance with the National Electrical Code, which allows for multiple conductors to share a common raceway, provided that certain conditions are met. Firstly, the conductors must be of the same size and insulation type. Secondly, the conductors must be properly bundled and secured within the raceway. Thirdly, the conductors must be protected from physical damage. Fourthly, the raceway must be large enough to accommodate the conductors without overcrowding. In this case, the conduit between the two busway disconnects and the common conduit run to the two three-phase motor circuits would need to meet these requirements. It is important to note that the National Electrical Code does not specifically address the use of busway disconnects in this type of application. However, the general requirements for multiple conductors in a common raceway would still apply. It is also important to ensure that the busway disconnects and the conduit are properly rated for the current and voltage of the motor circuits. It is recommended to consult with a qualified electrician to ensure that the installation is compliant with all applicable codes and standards. When considering running conduit between busway disconnects to feed multiple motor circuits, several factors must be carefully evaluated to ensure compliance with the National Electrical Code and safe operation of the electrical system. Firstly, conductor sizing is crucial. The conductors within the conduit must be appropriately sized to handle the ampacity requirements of each motor circuit. National Electrical Code Table 310.15b16 provides guidance on allowable ampacities of insulated conductors based on insulation type and temperature rating. The selected conductor size must have an ampacity equal to or greater than the motor's full load current, as well as any applicable overcurrent protection device ratings. Secondly, overcurrent protection is paramount. Each motor circuit must have its own individual overcurrent protection device, typically a circuit breaker or fuses, sized according to National Electrical Code Article 430. These devices protect the motor and conductors from overload and short-circuit conditions. The overcurrent protection device rating should not exceed the conductor ampacity or the motor's nameplate rating. Thirdly, conduit fill must be calculated. National Electrical Code Chapter 9 provides tables and guidelines for determining the maximum number of conductors permitted within a specific size of conduit. The conduit fill calculation must account for the size and number of all conductors within the conduit, including equipment grounding conductors. Overfilling a conduit can lead to overheating and insulation damage, increasing the risk of electrical faults. Fourthly, equipment grounding conductors are essential. An equipment grounding conductor, or earth, must be included within the conduit to provide a low impedance path for fault current back to the source. This ensures that in the event of a ground fault, the overcurrent protection device will trip quickly, minimizing the risk of electrical shock. The size of the equipment grounding conductor must be determined based on the size of the circuit conductors, as specified in National Electrical Code Table 250.122. Fifthly, bonding is important. All metallic components of the electrical system, including the busway disconnects, conduit, and motor frames, must be properly bonded together to create a continuous electrical path to ground. Bonding helps to equalize potential differences and reduce the risk of electrical shock. National Electrical Code Section 250 provides detailed requirements for bonding electrical systems. Sixthly, short-circuit current rating must be considered. The busway disconnects and other components within the electrical system must have a short-circuit current rating adequate to withstand the available fault current at the installation location. This ensures that the equipment will not be damaged or cause a safety hazard in the event of a short circuit. A qualified electrical engineer should perform a short-circuit study to determine the available fault current and select appropriately rated equipment. Seventhly, labeling and documentation are crucial. All components of the electrical system, including the busway disconnects, conduit, and motor starters, must be clearly labeled to identify their function and voltage rating. Accurate documentation, including wiring diagrams and panel schedules, should be maintained to facilitate troubleshooting and maintenance. Eighthly, coordination with local codes and regulations is important. In addition to the National Electrical Code, local building codes and regulations may impose additional requirements for electrical installations. It is essential to consult with the local authority having jurisdiction to ensure compliance with all applicable codes and regulations. Ninthly, professional installation is highly recommended. Electrical work should only be performed by qualified electricians who are familiar with the National Electrical Code and local codes. A professional electrician will have the knowledge, skills, and experience to ensure that the installation is safe, reliable, and compliant with all applicable requirements. Tenthly, regular maintenance is essential. Electrical systems should be inspected and maintained regularly to identify and correct any potential problems. This includes checking connections, tightening terminals, and testing overcurrent protection devices. Regular maintenance can help to prevent electrical faults and extend the life of the equipment. In summary, running conduit between busway disconnects to feed multiple motor circuits is permitted under the National Electrical Code, provided that certain conditions are met. These conditions include proper conductor sizing, overcurrent protection, conduit fill, equipment grounding, bonding, short circuit current rating, labeling and documentation, coordination with local codes, professional installation, and regular maintenance. By carefully considering these factors and consulting with qualified professionals, it is possible to create a safe, reliable, and compliant electrical system. The National Electrical Code, or National Fire Protection Association 70, addresses the installation of electrical conductors and equipment. Several sections within the code would be relevant to the specific scenario of running conduit between busway disconnects to feed two three-phase motor circuits. Firstly, Article 300 of the National Electrical Code provides general requirements for wiring methods and materials. This article covers topics such as protection against physical damage, securing and supporting wiring, and the use of approved materials. Secondly, Article 310 of the National Electrical Code addresses conductors for general wiring. This article includes requirements for conductor ampacity, insulation types, and installation methods. Table 310.15b16 is particularly important for determining the allowable ampacity of conductors based on their size and insulation type. Thirdly, Article 314 of the National Electrical Code covers outlet boxes, conduit bodies, and handhole enclosures. This article specifies requirements for the size and construction of these enclosures, as well as the number of conductors permitted within them. Fourthly, Article 344 of the National Electrical Code addresses rigid metal conduit, or rigid metal conduit. This article specifies requirements for the use of rigid metal conduit, including its installation, support, and grounding. Fifthly, Article 348 of the National Electrical Code covers flexible metal conduit, or flexible metal conduit. This article specifies requirements for the use of flexible metal conduit, including its installation, support, and grounding. Flexible metal conduit is often used for short runs to connect motors and other equipment. Sixthly, Article 350 of the National Electrical Code addresses liquid-type flexible metal conduit, or liquid-type flexible metal conduit. This article specifies requirements for the use of liquid-type flexible metal conduit, which is suitable for wet locations and other harsh environments. Seventhly, Article 368 of the National Electrical Code covers busways. This article specifies requirements for the installation and use of busways, including their support, grounding, and overcurrent protection. Eighthly, Article 430 of the National Electrical Code addresses motors, motor circuits, and controllers. This article includes detailed requirements for the protection of motors against overload, short circuits, and ground faults. Ninthly, Article 250 of the National Electrical Code covers grounding and bonding. This article specifies requirements for grounding electrical systems and equipment, including the use of equipment grounding conductors and bonding jumpers. Tenthly, Chapter 9 of the National Electrical Code provides tables and examples for calculating conduit fill. These tables specify the maximum number of conductors permitted within a specific size of conduit, based on the conductor size and type. In addition to these articles, other sections of the National Electrical Code may also be relevant, depending on the specific details of the installation. It is essential to consult the latest edition of the National Electrical Code and to consult with a qualified electrician to ensure compliance with all applicable requirements. To elaborate further on the specific requirements mentioned, consider conductor ampacity. National Electrical Code Table 310.15b16 provides ampacity ratings for various conductor sizes and insulation types. For example, a number 12 American wire gauge copper conductor with type THHN insulation has an ampacity of 30 amps when installed in a raceway with no more than 3 current carrying conductors. The ampacity must be derated if there are more than 3 current carrying conductors in the raceway, as specified in National Electrical Code Table 310.15 colon. With regards to overcurrent protection, National Electrical Code Section 430.52 specifies the maximum size of the overcurrent protection device for motor circuits. For example, the overcurrent protection device for a motor with a full load current of 20 amps should not exceed 250% of the full load current if fuses are used, or 300% of the full load current if inverse timed circuit breakers are used. Concerning conduit fill, National Electrical Code Table 1 of Chapter 9 specifies the maximum percentage of conduit area that can be occupied by conductors. For example, the maximum fill for a conduit containing 3 or more conductors is 40%. With regards to equipment grounding, National Electrical Code Table 250.122 specifies the minimum size of the equipment grounding conductor based on the size of the circuit conductors. For example, a circuit with number 6 American wire gauge conductors requires a number 10 American wire gauge copper equipment grounding conductor. In terms of bonding, National Electrical Code Section 250.92 specifies the requirements for bonding metal enclosures and equipment. This section requires that all metal enclosures and equipment be bonded together to form a continuous electrical path to ground. When it comes to short circuit current rating, the busway disconnects and other equipment must have a short circuit current rating adequate to withstand the available fault current at the installation location. This rating is typically expressed in amps or kiloamps. Lastly, with labeling and documentation, all components of the electrical system must be clearly labeled to identify their function and voltage rating. Wiring diagrams and panel schedules should be maintained to facilitate troubleshooting and maintenance.